Thank you all for coming. My name is Dr. Tyler McGaughey. I work here at WVCTSI here in the Biostats Epidemiology Research Design Core. I want to acknowledge my co-host, Emily Kemper. Emily is taking care of the meeting and letting folks in. So if you have any trouble, go ahead and ping Emily Kemper, and she'll help you resolve any technical issues. I'm going to go ahead and get started. So, if everybody could for me really quick, just for attendance, drop your name in the chat. If you would like CE credits for today, go ahead and put CE and your email behind that. That way I can email you the CE form for your professional development. So I'll give you guys a minute to do that. Today is a pretty open, laid-back lecture like I like to do for most of my talks. You're more than welcome to jump in with a question anytime, raise your hand. We can take a quick break and answer that. And if you think you have a weird question or you feel like it's a dumb question, you can message me or Emily Kemper directly, and we'll answer it as an anonymous question. There are no dumb questions today. This is really designed to be a complete entry-level class. So like I saw one of our colleagues, Dylan works a lot on our AI ML. So this is definitely not designed for anybody with that level of like expertise in coding. We're going to go from the very, very entry level, talk through some computer terms and how this can really benefit your research. I do need to acknowledge my two co-authors real quick. We have Mars, our tuxedo, and then of course Dexter, our one brain cell orange cat. Yeah, so with that, let's get started. So, what is high performance computing? High performance computing is a network of computers that are designed to tackle large problems. So we really look to high performance computing when we get to these big data problems that are too big for a single computer to handle. I know a lot of times my computer can barely run a meeting like this and send slides right now. I've propped up with a couple TV remotes trying to get some air to it. So that's where these high performance computing clusters come into play. So the next big question, why in the heck should I care? Research projects every day are getting larger and larger with their data. So the example I always give is with my functional brain scan work, we take 10,000 samples of the brain every 2 seconds. And then over 10 minutes, you can see how that adds up. And then times that by 20 or 30 patients and a beginning and a follow-up scan. And you see how we get to hundreds of thousands to millions of data points pretty darn quickly. Or like I saw Ranjita and Anahita on the call, they're working on a great Alzheimer's project with thousands of patients' images and all kinds of data points. And I know they're actually going to use this resource later on to analyze some of their data. It's also great for these machine learning, artificial intelligence programs. Dylan is using it for some web-based text scraping, trying to match some researchers with some NIH grants. And it's really here to help speed up your research. It's a pretty powerful computer and allows us to develop these huge in-depth models pretty quickly. So now we're going to take a couple steps back into the 1970s, get some disco out, and we're going to talk about how HPCs came about. I know most of you guys on the call, and I know this won't shock you, I actually have one of the computer chips from this computer that sits on my desk. This was Cray 1. This was built for the Los Alamos National Labs, built in 1975, and it was the first well-documented supercomputer. The processors on this guy ran at 80 megahertz, and it had 8.39 megabits of RAM per core. Just for reference, your iPhone that's in your pocket right now has 6 gigabytes of RAM, and its main processor runs at 3.4 gigahertz. For those of you guys who can't do math as on the fly, like myself, that's about 40 times faster or more powerful than that supercomputer, just your little iPhone in your pocket. And so we've come a really long way over time with our computing power. But we've run into something called Moore's Law. So this is kind of a plot on the x-axis of time and y in just pure quantity. So you can see here, we've kind of plateaued in both power and the frequency of how fast a computer chip can work. Um, Most of our modern computer chips work around 3.5 gigahertz. Anything faster than that, we get into what we call turbo clocking, but we reach a thermodynamic problem. You start melting your computer. They get too hot. We can't get the heat off of them. Turbo clocking, some of the gamer guys do it where they'll turn off some cores to speed a couple up, and we still end up with heat problems. The only way we're able to make computer chips faster now is we're trying to get more and more transistors on the board. And we're slowly reaching that limit with these micro transistors. And so that's why we're looking to quantum computing. We're not there yet. Once the physics folks who are significantly smarter than me figure out how to get them to quantum computing, then we won't have to worry about heat as much. But right now we are kind of at the limit of what we can do with computer chips. And so this is how we fix this problem. Excuse me. This is where HPCs come into play. We work on parallel computing or distributive computing. So like my really nice desktop computer that I use to process radiological images, let's say it can process 2 patients at a time, and it takes me 20 minutes to process a single patient. So every 20 minutes, I have 2 patients done, and I go to the next 2. That would take me forever to process a lot of our modern studies with several hundred patients. And so that's where the HPC comes into play. The HPC is a network of a whole bunch of computing nodes that are able to tear through hundreds of patients at a time. And so we run those in batches. I tell folks, think about like batches of cookies. We'll run 80 patients at a time, then run another 80 patients, and things like that. And it can process a lot more patients at the same time. So we finish these jobs in a couple hours as opposed to a couple weeks. I remember my dissertation data. I had 32 patients, brain scans before and after. It took that code about a week to run on my grad school computer, and it was very cranky the whole time. Running a study bigger than that in the HPC now only takes a couple hours. Any questions so far? Okay. Just a quick reminder for anybody who's joined us a little late, please drop your name in the chat for attendance purposes. And if you need CEs for the day, we are offering continuing education credit. Please drop a CE after your name and your email so I can email you that CE form to get you some credit for the day. So we're going to talk through some basic computer anatomy. Like I said, I don't want the HPC to be a quote unquote black box. You dump data in, you get a cool AI model out. We're going to actually get into some of the nitty gritty things. So this is something that gets thrown around a lot. What is a CPU? A CPU is really the brains of the computer. It stands for the central processing unit, but this is what's actually doing those logarithmic or algorithmic calculations line by line. So the clock speed is what we can think of kind of like a heartbeat. It's how many commands it can execute per second. And most of our computer chips today are multi-core. And so when you hear things like, oh, I have a 4-core computer chip, I have a 16-core computer chip, that's how many commands it can execute at the same time. And then we talk about the number of threads. And so threads are like a line of commands going into a CPU. And so we might have a multi-thread, multi-core processor. And so, like I said, we're kind of reaching the thermodynamic limit right now on computing chips. And so that's why we bring more chips into the fray. RAM is the next thing we're going to talk about. This stands for random access memory. The CPUs, or the brain of the computer, is only able to store just a little bit of memory. I'm talking about a couple megabytes or so. And this is kind of what we call the working memory. You can read in or read out in any order. I jokingly pretty often go, I want to upgrade my working memory. To correlate to humans, think about like your running to-do list in the day for what you have to do today. Oh, I have to go grocery shopping, get the dry cleaning. I need to go to Kroger, things like that. But this is not designed for long-term storage. RAM has to have power, so as soon as you turn your computer off, RAM's wiped. And we'll talk about long-term storage here in a second. This memory is significantly faster than your traditional long-term storage, but it's where the computer holds a lot of those temp files. And this is normally on the gigabyte range. So there's 1,000 megabytes in the gigabyte. So this is normally 30 or 40 times more than most CPUs can handle. And then the next to last thing I want to talk about is what we consider long-term storage. Nowadays, we use solid state drives, and we're moving towards NVMEs, non-volatile memory expansions. These are significantly faster than the good old hard drive disks or even the floppy disk back in the day. They can read write about 3,500 megabytes per second. And we set them up in what we call a RAID fashion. There's a bunch of different RAID strategies, but this is the redundancy pattern. So on our current cluster, we could totally lose a whole drive, like it could just blow up or get shorted out or something, and you wouldn't lose any data. It's because we stripe the information across a whole bunch of different drives, and so that's how we build in fault tolerance. Our goal for working memory and long-term storage is what we call 4 nines of stability, so 99.9999 of data storage and replicability. And so that's why we work in these RAID fashions. The last thing I want to talk about are good old GPUs. These are graphic processing units, or once we get into higher speed computing, we call them graphics accelerators. These are specially designed boards that go into the main boards that only focus around images. And so if you have that nephew or niece or somebody who's really into playing Fortnite or one of these modern games, they're talking about frames per second and lag rates and latency rates. These GPU cards are often $20,000 to $30,000 for our servers, as opposed to the consumer version, which is a couple hundred to $1,000. The whole purpose here is to deal with images and manipulate them and process them. And so, like on our cluster, we have 2 nodes that have these very fancy GPU units that I use quite a bit for like the visual machine learning and projects like that. So now we put it all together. This is what a single node inside our cluster looks like. These nodes will have some local storage, normally around a couple terabytes. They'll have, which are in the form of SSDs, a bunch of RAM and to the tune of several hundred gigabytes, a handful of CPUs to actually do the work, and some of them some of them have graphic accelerators as GPUs, some of them don't. And then there's some other network accessories along with our HPC cluster. And so we'll look at this diagram really quick. This is what the CTSI high performance computing cluster looks like. Just a quick note, there are 2 other WVU high performance computing clusters. Those are maintained by the downtown folks out of the High Performance Computing Center. They also help run ours with a lot of the expertise there. The main difference is ours is HIPAA compliant, and the 2 downtown platforms are much larger, much stronger, but they are not HIPAA compliant. And so obviously with a lot of our clinical and translational science data, we need to run patient-based data. And so that's why it's great that we have this HIPAA compliant resource. So in addition to the nodes that we'll talk about here in a second, we have some other supporting things. So like we have a network rack that helps us talk back and forth to this cluster pretty quickly. And then like a storage array, which is for more of that long-term storage. So when you set up your job, it'll push the code it needs and the data it needs to one of these compute nodes. It'll work on it, and then it'll dump it back to one of the long-term storage nodes. So just going through this diagram really quick. This is the basic overview of our cluster. So inside one of these boxes is a whole node itself. And a node contains a couple CPUs and some RAM. Okay. Once you first access the cluster, you're going to hit one of these 2 head nodes. We call those head nodes or login nodes. Think about it like the doorway. And so once you get in there, this is what you'll interact with, set up your jobs, and then it'll get pushed out to a compute node. One of the things we need to be very, very careful of is not running heavy intensive process on these login nodes. So think about it. Think about this like a doorway. If somebody is standing there working in the doorway, it's a pain in the butt. You can't get to other resources inside the area. You can't get to the other nodes. So that's why it's important to remember when we set up a job, we want to push it to one of the compute nodes. So as you can see here, we have 5 dedicated compute nodes. These are super strong computers, and you can call up as many of these nodes as you need. You can even take the whole cluster if you need it. But these are good for run-of-the-mill tasks, computational models, things like that. We have what we call big mem or big memory. this is the one with a whole lot of RAM. So if you're doing a really, really random memory intensive project, an example for me is skull stripping. So like obviously there's not neuronal activity outside of the regular brain. So we'll go through and remove the patient's skulls we work. That's a mathematical model that figures out the dura around the brain and then removes the rest of it. That's a very, very intensive project because you have to store a lot of temporary files. And so a lot of times I'll call up this big mem node to run those projects. The last two you can see here in green are our graphics nodes. And so this is great when we're doing things like machine vision, visual machine learning, things like that. We can call those GPU, those graphic accelerators in to take care of those image-based problems. And again, for most projects, you can call any node, like just because it has graphics cards doesn't mean it can't do normal tasks, or just because it has a lot of extra memory, it won't hurt to run your job. And remember, the big advantage here is our cluster is HIPAA compliant, unlike the two downtown clusters. But the downtown clusters are much bigger. Some general terms that I've hit today that I just want to kind of review really quick. A cluster is a bunch of nodes working together. A node is one of those single computing units. Batch is something I talk about a lot. I'll explain this picture. When I think of a batch, I think about making batches of cookies with my grandmother. This is my lovely grandma, Chris. And I was being sassy at dinner for some reason, and she was trying to stab me with a fork. And so that's how we talk about, we'll make one batch of cookies or one set of computational jobs, and we'll go to the next. And the last one is a GUI. This is called a graphical user interface. And so this is what helps us translate between what looks pretty to the human eye and basic computer language. And so this is kind of that click and point system to go through things like a normal web page. Okay. What are some good use cases for the high performance computing cluster? So we're slow as humans. Computers can do things hundreds of thousands of times faster than we are. And so to really take good advantage of a high performance computing cluster, we want to write code that stands alone. I don't want to write code that has to wait for me to click OK or go to the next step. We want to kind of set up our job to where it'll run all the way through by itself and spit out whatever else for the next step. It's also really good at repetitive jobs. And so this is where I say things like, oh, I have to run 200 patients, but I want to process them all the same way. You can also work on these large data sets and large complex problems that you can break down into smaller projects. And so maybe it's looking at the first stage of pre-processing, then root processing, and then maybe a later model. And so things that can work independently, and then we mesh the results together and then work on the next step. An example of that. So great. Hopefully you're now all kind of excited about high performance computing. You understand what's going on. How do you get access, right? This is a HIPAA secure computing platform. So there are a couple steps that you need to go through to get to the resource. You will need to log in through our iLab at wvucorefacilities.org and request an account. It's just as simple as filling out the high performance computing request. And at the very end of this talk, I'll put up all of our contact information. Excuse me. You can email any one of us, and we're more than happy to help you get set up and talk you through the process. Amber Abel is one of the project managers here. She is great with iLab. So are Sharon, Patrick, and Emily Morgan. They're more than happy to help you get through any bugs that you may encounter there. After that, we'll go out to the high performance computing team. They will set up your account and will email you instructions on how to get into the cluster. There are some connection requirements. So the HPC actually lives here in Morgantown. It's housed at the Secure Data Center. With that being said, it is a secure network resource here, which means you can access it a number of ways, but it has to be through the WVU HSC system. So you can use the WV Virtual Private Network on site here at the HSC with Ethernet or HSC encrypted Wi-Fi, or through the new Azure Virtual Desktops, which did replace VMware for those of you who are not up to date. With that being said, if you're one of our partner sites, thank you for joining us. let's talk by email. There are some case-by-case things that we need to figure out, like size of the data, does it need to be DUA, things like that. Again, email us, and we are more than happy to chat with you through that process. Great. Now that you've gone through the steps to get your account, how do you actually get into the darn cluster? And so this is the login or the login website, ctsi-hpc.hsc.wu.edu. And you'll log in with your normal HSC credentials. So I'm going to talk you guys through a couple of the pages you'll see once you get in, and then we're actually going to jump into some live demos where I'm going to walk you through the cluster in real time, and I'm here for questions. So one of the most important pages you'll come to is your home directory. Think about your home directory as your filing cabinet. This is where you can make different files, drop your data, and things like that. One of the things I want to note is the HPC isn't really designed for long-term storage. The capacity on the HPC is about 40 terabytes or so. But if all of us stored all of our data there, we'd obviously run out of space kind of quick. So there's 40 terabytes. That's great for archiving some projects and results. But if possible, we encourage you to download it to secure network drives like the Y drive. If you're able, if not, and you have a specific project that needs to stay archived in the HPC, we can talk about it and it's perfectly fine. But as a habit, please make sure you're downloading your data after you completed it. So the command line interface, this is built for speed. This is what we think of when we think of the terminal. It's not terribly user-friendly. There is no click and point. You do have to do what we call hard coding, where you're typing and hitting enter every so often. But this is the fastest way to run code. And so a lot of times folks will build their code on their local computer, and then they'll upload their code and their data to the HPC, and then they'll just call the script and execute it. One of the big things is if you log in through the command line interface, you will be on a head node. One of those login doors, one of the login nodes, or like that doorway I talked about. We need to make sure we're queuing up Slurm. Don't worry if you don't know what Slurm is, we'll talk about it in a minute. And get off those head nodes and actually send your job to a compute node. But yes, there is an easier way for those of us who don't like to hard code. There are several different GUIs or graphical interfaces that you can jump to, whatever you're comfortable with. We have the virtual desktop that you can see here that is more click and point. It is set up like a Linux desktop, but don't let it scare you. We are more than happy here to help walk you through things, give you demos, help with your code, whatever you need. We also have good old RStudio, and as you can see down here, we have Jupyter Notebooks. So I mentioned Slurm. I don't know if I have any other fellow Futurama fans, but unfortunately it's not the cool drink from Futurama. Slurm is our workload manager. I tell folks it's the triage nurse or it's the traffic cop. It helps us manage resources in real time. So when we queue a job, we submit it, we submit our Slurm script, and then Slurm takes over. So like if I only need to run one node and Emily Kemper also needs to run one node, it might run our jobs in parallel on each node. But if Dylan is doing a big scraping project, Dylan needs all the nodes. It'll probably wait till all of these small little jobs are done, or it might hold it till 2 a.m. or 3 a.m., just depending on who's working in the cluster at that time. It makes the most use of the resources at hand. And then this is something it does automatically in the background. Most of the time, there's little to no wait on our cluster, unlike the downtown clusters. Most of the time, the downtown clusters are used for a lot of really large programs like satellite mirroring and theoretical models. Sometimes those will have a 4 to 6 hour wait, but we pretty rarely have one on our HPC. There are quite a few software packages pre-built out on the HPC. The base operating system for HPC is Linux Red Hat, which is not as scary as it sounds. There's just some funny little quirks that you'll have to learn switching to Linux. There's all kinds of Python libraries pre-built. There's AI and ML packages built like TensorFlow and PyTorch. I'm pretty sure every kind of imaging processing software you can think of. There's SPM, AFNI, FSL, and even MATLAB. And more importantly, if it's not already on the cluster, we are more than happy in coordination with the HPC, the high performance computing folks, to build that software and push it out to these compute nodes. That's one of the other advantages of the clusters. Um, we have distributed computing, which means you can send your job to any node and it has the same software all the way across. And so you don't have to call back to the head node to get the software to pull down the compute node and vice versa. Okay, so now we're going to switch gears for a little bit. I'm actually going to jump into our HPC and walk you guys through some of the things we just talked about. So bear with me for 1 second while I stop sharing and get everything pulled over. So let's see if we can do this. Okay. Emily, can you just give me a thumbs up? This looks okay. Great. Okay. So after you get logged in, this is what the landing page looks like. That's our great logo. But more importantly, there are all kinds of useful documents down here. Can you see my cursor?
Yes.
Okay. So this first link right here has a bunch of docs out in the Google Doc that can walk you through a lot of the steps if you want to try to work through things. Here's the link to the high performance computing specific help desk. This is different than the regular IT help desk. These are our computational theory guys like Guillermo and Aldo from downtown with years and years of expertise. And I guarantee you, if they can answer your question, they know a guy. They are really, really good at their job, and they're always super nice and super helpful. We defer to them quite a bit. They're obviously the experts once we get past our kind of entry-level knowledge here at CTSI. And then here's just a quick breakup if you ever need to cite any of the resources here. But that's all that's on the homepage. Okay, and then the next tab I'm going to show you guys really quick is the home directory. And so like I just said, this is where you can upload and download your data. And so this pops up just like a normal file explorer, and you can browse to your folders and upload data. There are high-speed links here between the HSC and the data center, and so it is pretty quick uploading data back and forth. The next thing you can jump to is cluster. And so this is where we get the kind of command line interface. So by default, nothing is enabled on the cluster, right? Because all of the programs we run every day in the background, especially Microsoft Teams, tends to slow down your computer. And so if you need to call a certain software package, like if I want to load MATLAB, I just type in module load MATLAB. Okay, now MATLAB's running. I'm sure my friends up in the Grisenko and Yakovenko lab are happy to see some MATLAB. And for those of you familiar with MATLAB, this is obviously not what the MATLAB homepage looks like. But if we do a really hard math problem here, you can actually see that we have the MATLAB functions pulled up. Okay, let me get you this panel out of the way. We'll go back to that really quick. If you're curious about what modules are available, what patches are available, it's just simply module available. And then this is going to list out all of the different packages that are already preloaded on all of the nodes here in the cluster. Obviously, for some of us with less coding experience, this is a scary looking interface. And so that's where we get into what we call our interactive apps. And here are your three main choices: our Jupyter Notebook, our RStudio server, and our CTSI desktop. Like any cooking show, I've already pulled up these really quick. This is our standard Jupyter Notebook. And so we do something like print. Hi, folks. It'll execute our code for us. And you can save this and refer back to it like you would any other Jupyter session. See, like I can create a new notebook really quick. And it'll ask me what language I want to use. Yes, like this one's open in Python 3. Okay. This is what the CTSI virtual desktop looks like. And so this is a little more point and click. So I need to module load Slurm, our job. So this will look a little more familiar to you guys. If you want to get that nice graphical interface, we'll give it 1 second. here to load. And so see, this looks a little more like the MATLAB we're all used to. And here you can build your code. And then since I've already loaded Slurm in the background, we can actually submit our jobs out to Slurm. It'll send them out to all the compute nodes or the GPU nodes, whatever we specify, and actually start running our code there. Okay. One other thing I want to show you guys really quick is how do we actually get there? So, and I need to hide meeting rituals. Okay. So now we're going to go through and actually look at launching a session. So all I've done is interactive apps and then pick the one I want to open. So we want to open a CTSI desktop. Here's where you specify where you want your jobs to run. So we can call big mem for the one with a lot of RAM, GPU here if we need a graphic accelerator, or defq is just the default nodes. And then this is how many CPU cores you need. The defq have 40, 48, or 80 cores, depending on whether you're calling a whole node or a partial node. Big mem has 80 CPUs, and the GPU nodes have 40. And obviously, if you go over one of these, that's fine. It's just going to call up multiple nodes for you to run. And then here's how many hours you need to run. You are limited to 23 hours, 59 minutes, and 59 seconds. Slurm will not let you run a job for 24 hours. And I don't think we've ever encountered a job that we need to run for more than a couple hours. And the other nice thing is you can actually get an email when it starts. So for little jobs, if you're only needing 40 or 80 CPUs, they spin up pretty quickly, like we can do this one in real time. But if you're going to call up a couple nodes where you need several hundred CPUs, it's going to take probably 10 or 15 minutes. And this will ping your inbox really quick and see this job just executed. And so now I'm ready to go to my CTSI desktop. That's how quick it is to spin up a session. I think that's all I wanted to show you guys today on this. Give me 1 second. We're going to switch back to PowerPoint. Okay. Can you see slides again? Great. Okay. So great. What are some of the takeaways that I want you guys to get from the day? There are 3 high-performance computing clusters for you all to access. The main difference with our cluster is it's smaller, but it's HIPAA compliant. We have a team of experts here to meet you wherever you are. So there are folks here in CTSI to help you with some of the basic questions, getting set up and developing your code. And then we also have access to some of the folks downtown, some of those experts to really help you dive into your code and optimize it for the HPC. I hope you realize that the HPC is really here to speed up your research. And it's a pretty robust, accessible resource available anywhere on the HSC campus or offsite through some of those virtual options we talked about. But the big thing is start the conversation. We are here and more than willing to help you with any problems you have, even questions. And to that end, I will give you guys our contact information. My email is the first one here. I'm more than happy to have coffee, a casual environment if you want to talk through an idea. There's the generic or vanity birdcore email that comes to a lot of us here on the team, and we can help direct you to the right person. And then there's Amber's email. Hey, Amber, there's your email. I forgot to say I was putting it up here. But Amber will help you if you have any iLab troubles and setting up your account. Then I also want to point you guys to the high performance computing website. And that is where there's a lot more information and background and kind of specifics on all 3 of the clusters.